In this video, we're going to be talking about the force of air resistance. This is what I've called F sub AR, AR for air resistance, so I haven't written far here. This is the force of air resistance. And we can probably figure out some things about this force just by thinking about it. It's always a good idea to think through physically what's happening to see if we can get an intuition of how the math is going to work. So let me draw this symbol. This is the mathematical symbol for proportionality. So what I'm saying is the air resistance force is proportional to some things. And let's see if we can just think and figure out what these things are going to be. Well, the first thing I can think of is if we're looking at the air resistance acting on an object, is going to be the cross-sectional area of that object, which I'm going to call A. To see why this is the case, let's just think. Let's imagine that you're in your car and you're driving down the freeway and you stick your hand out of the window, right? Like this, like I have pictured with your hand open. Forgive the poor artistic skills, but this is the idea. Your hand is open, your palm is facing the wind, right? The wind that you feel coming from driving whatever speed you're driving. So let's put some numbers to this. Let's say that you're driving 70 miles per hour and you stick your hand out. Well, most of you watching this video have done that at some point, and you recognize that you feel a pretty significant force on your hand. At 70 miles per hour, it's probably going to push your arm backwards a little bit, right? Well, what if instead of opening my hand like I have pictured, I turn my hand to the side, right? So my hand is now flat, my palm is facing the ground, and what I have done is I've reduced the area of my hand that I'm presenting to the wind, right? And if you do this, you will notice that the force on your hand goes down significantly. It's still there. There's still a force. You're still doing 70 miles per hour with your hand out the window, but the force is by far less than it was when your hand was open. Right? So this is what we mean when we say cross-sectional area. What I've done is I've reduced the amount of surface area that I'm presenting to the wind or the air that's causing this force. Okay? All right. Next thing I can think of is, let's go back to my man in my car. Let's give me back his open hand. All right. So now, instead of driving 70 miles per hour, let me drive 10 miles per hour. And you can probably imagine, again, most of you probably have done this, the force you feel is not that significant. At 10 miles an hour, you feel a pretty small force. But a while ago, when we were driving 70 miles per hour, we said that we felt a really large force. At 10 miles per hour, we have a small force. 70 miles per hour, we feel a large force. So it seems to me reasonable to say that the force of air resistance is proportional to the speed with which the object is traveling. As it turns out, if you perform an experiment on this, you will find that it's actually proportional to the speed squared. But our thinking about it is still valid. The faster I go, the bigger the force gets, right? I can think of one more thing, and that is the density of the material through which I'm moving, right? If I'm in air, I'm calling this air resistance, well then that would be the density of the air. So this is a term which I'm going to signify with the Greek letter rho. It's a traditional letter for density. To see why this is the case, let's move past our man in the car and let's get on a boat. Okay? So let's say that this boat is traveling 20 miles per hour. And you stick your hand out, as you did in the car, in the air, and you feel somewhat of a force, but it's not really, really large, right? Okay, that's well and good, but now, what if you go a really long arm, and you stick it down in the water, right? This poor guy's arm is all kinds of hurt right now, but you see what happens, right? The force you feel is immediately much, much, much greater. That's because the water is more dense than the air. So I think the force has to also depend on the density. And then if we really want to make this mathematically correct, we can erase our proportionality sign and replace it with an equation sign, but when I do that I have to find a proportionality constant. which I will call D in this case. Most people call this the drag coefficient. It's going to be something that's a function of the material, right? And just a function of the construction. You know, if there, a lot of people make a lot of money by determining how to make the drag coefficient on cars and airplanes really low to make them more aerodynamic. But it's just a fact, if you have a really rough piece of sandpaper and a really smooth piece of glass, the sandpaper is going to experience more air resistance than the glass because it's going to have a higher drag coefficient. So this is what we have. The air resistance is proportional to some drag coefficient, the density of the medium, the cross-sectional area of the object, and the speed of the object squared. So notice, first of all, this is different than the normal friction from a surface that we've looked at, because that did not depend on a speed at all. But this force does depend on a speed. Alright, so let's see how this works in practice. Let me take an object. Let me get to a fresh sheet. Let me take some sort of object. Doesn't really matter what it is. We'll say it's a box. And let me drop it in air. So I'm going to drop it from a great height so it has lots of time to move. And so if I want to look at the forces acting on this thing, the second that I drop it, right, it hasn't had a chance to start moving yet. Its velocity or its speed is still 0. But I do know that there's a force on it, which is the force of gravity, which is calculated as mg. Right? The mass times the acceleration due to gravity, 9.8 meters per second squared, or in the English system, 32 feet per second squared, or some people say 32 feet per second per second. At any rate, this is the force of gravity, and notice that it's constant. Little g doesn't change, the mass doesn't change. This is a constant force. So this force never ever changes. However, the second that this object starts to move, it experiences a force of air resistance. And let's remember that resistance is proportional to speed. Now the area of this object's not changing, the density of the air is not changing, the drag coefficient's not changing, but the speed is changing. And so immediately after this thing starts to accelerate, once it's picked up a little speed, I start to get a little force of air resistance, right? So this is my force of air resistance. But of course, as I let this go on, it picks up more speed, and so let me erase this. And so as it picks up more speed, the air resistance gets bigger, right? Picks up a little bit more speed, the air resistance gets even bigger, to the point where as it approaches what we would call a terminal velocity, the force gets big enough to exactly match the gravitational force that's pulling it downward. At that point, my forces cancel, right? And I can say that the sum of the forces is 0, which means I am in equilibrium. So I will continue to move, of course, at whatever velocity at which I've arrived, but I will not accelerate any farther. So this is what we call terminal velocity. For humans, this is somewhere around 110 miles per hour. But for other things, this is very different. Notice the force of gravity depends on the mass. So if you have a really massive object, you have a really big gravitational force, and you've got to develop a really large force of air resistance to counteract that, which means it has a really high terminal velocity. If you have a really low mass, you have a really low force of gravity, which means you just have to develop a small force of air resistance. This is why if you were to jump off a very tall building and right next to you your friend were to drop a cockroach off that building, you would splatter on the concrete and the cockroach would not, because the cockroach is so light it reaches terminal velocity almost immediately. You just have to develop a very small force of air resistance to counteract gravity, and so the cockroach just gently floats down. This is also something you see with things like feathers. If you've ever dropped a feather or a piece of paper, they don't crash into the ground and leave holes. They float gently down, and it's because they're so light that the air is, and plus they have such a large surface area, that the force of air resistance equals the force of gravity acting on them almost immediately, and their terminal velocity is very low, and so they just float gently down to the ground. Right. I should mention that on one of the Apollo moon landings, they actually performed an experiment where an astronaut dropped a geologist's hammer and an eagle feather, And on the moon, in the absence of air resistance, they both hit the ground at the same time. Right? So the idea that things fall at different speeds is true, but it's not because of gravity. Gravity's constant. It's because of the air resistance and how that changes for different objects.